So now we'll look at how to discretize this equation now that we have got it and solve it. Okay. So for discretization, the first thing that we've already seen as discretization involves splitting it into elements, right? So this is breaking up into elements. The old word we had used for it was segments, okay? So but we are calling them elements now. Okay. In 1D we can call them segments. In 2D what do we call it? We call them elements also, but the act of breaking up a domain into little triangles or squares or whatever is called tessellation. So that's another word you will hear. So breaking up is a sort of a colloquial word. The more technical word you will see in the literature is tessellation of the domain. Okay. So this we in 1D we already know what to do, break it up into segments, and the second part is we have to now introduce the basis functions or the shape functions in this case. Okay. So we already know what to do in terms of the basis functions. If I take one small segment over here, right, so this is some element E. These are the two nodes of this element over here. Okay. The global unknowns are u1 and u2 on this, let's say. Okay. And what is the local name that we will give for u1 here? So it will be u1 E is equal, right, just E, right, and this guy will be u2E. Is that right? Yeah. So here this again refers to left and this here refers to right. Okay. So I am writing this again so that you get used to this convention that we have. Okay. And this of course is global. Okay. So with this together, what do we have already discussed the basis functions. N1E is N1E is going to be 1 at x1 and 0 at x2, right. So what was the form of this? So x2E minus x2E minus x1E, right. So x1E less than x. We already seen this, and similarly N2E is going to be given by a similar expression. So what will N2E be? X minus x1E, right, for the same interval. Okay. Putting this together, I write the function inside over here, this u of x. What do I write it as? Yeah, we can call it a and 1, but we have defined the new variables over here. So I can write this as u1e times n1e x plus u2e n2e x, right. But this, see, okay, now let's pay a little bit of attention. The left hand side is u of x over what? The entire domain, right. So this entire domain which is existing all the way from, let's say, here to here. The term on the right hand side is non-zero in the eth segment. So how do I write a general expression for u? Multiply by pulse. We don't need to multiply by pulse because N1E already has the pulse notion inside it, because by definition I have made it 0 outside. So N1s are already, they already have the pulse inside it. Now I want you to give me a function u where I put in the value of x and it goes to the correct segment and constructs it as a linear combination of two shape functions. So, what remains to be done here? Summation, exactly, right. I have to sum over all elements, not nodes, right. Once so I go from the summation E is equal to 1 to, let us say, NE, if there are NE elements. So, every term in this summation is non-zero only in its own element. It does not spill over into the other element, right. It is like pulse basis function. So, it automatically, you give me the correct, give me any x you want, of these NE terms, only one expression will be non-zero in the segment of interest, and that is the term that I want. Okay. There was a even more compact way of writing this, right. So, what you could do is, you could write this as, keep this summation E is equal to 1 to NE and sum over what? What else do you think you can sum over? The nodes inside it, right. So, I can write I is equal to 1 to 2. So, what will this become? U I E N I E X. Even more compact. When we are doing this for some simple thing like a first order basis function, it does not really matter, right. But as I mentioned earlier, we can have higher order shape functions, where for a segment you need, let us say, 2 nodes, 3 nodes, 4 nodes, whatever, right. Those many number of nodes are required to specify a higher order polynomial. Then to write out this first expression over here becomes tedious, right. The summation is over every element. Now, inside each element, this number 2 that I have over here, this can vary depending on how much accuracy I want in the basis function. Okay. But this is more a implementation or coding issue to sort of give you more compactness in that. If it is not very clear, you can leave it for now. Okay. So, this is pretty much as far as this goes. This expression, as you can see, supposing I have another segment over here, it automatically takes care of everything, right. So, now that we have done this, let us see what is next is, now we have to take this guy and substitute into the weak form, right. In this equation over here, the previous equation over here, u was general, this u, right. Now, what I am going to do, now that I have got this form of u, I substitute it into this equation that I got. Okay. All right. So, let's do that. So, to generate this system of equations, what can I write it? So, first of all is u x is from before, right. So, I will write this once again, E is equal to 1 to NE summation I is equal to 1 to 2, right, and the remaining part was U I E N I E X. This is U. Okay. What about W x? W M x. What choice should I use for W M x? It is Galerkin's method. So, shape functions and testing functions are the same. So, what should I choose W M x as? N I E. So, remember, is the testing function fully known or does it have some unknowns inside it? If you go back to this equation, this is your step to look at this main big equation over here. Where do your unknowns go in? Which terms carry the unknowns? What is unknown in this equation? Is it W, P, U, Q, F? Which is unknown? U is unknown, that is what we want to find out. Everything else is known. So, therefore, W m is also known. I am going to choose it. I choose it to be equal to each one of the basis functions. That is Galerkin's method. Okay. So, let us come back to this. Now, what should I choose W m x as? So, you can see U x. What is unknown in U x? Which is the unknown part in U x? This guy, right? This guy is unknown. This guy is fully known because all that I need to know to specify this are the node locations which are known, because I broke up the domain into known node locations. So, what should W m x be? So question is, can WMX contain UI? Okay, so let's go back to this equation. So you are substituting this your unknown over here, which consists of U I E N I E X. This is what is being substituted for U. So the unknown is here. Now Wm is appearing over here, here and here. We said W should be known. There is no point in testing with an unknown something. So what should Wm be? If it contains a Ui inside it, as you are asking, a Uie, then what will happen to Uie in this equation? It will become second order. I'll get a Ui squared and those kind of things. But what is nothing is achieved by doing it. So what is left then? We cannot have N1 and N2 together in Wm. Is that what you're saying? Okay. So let's see. Let's go one at a time. Suppose, so do you agree that Uie should not be in WMX? Because it will be product of two unknowns then, right? So Uie should not be there. Then what is left? A known function Nie. So can I choose this to be NIEX? Is there any conceptual problem with this? Right. So if we go back to this equation, if I choose this WMX to be something like NIEX, is there any problem? This equation will contain the unknowns, Uies will appear at various places, and everything else will have to be done by integration, right? So, but you raised an important point. This choice of, we said that in Galerkin's method the basis functions and the testing functions are the same, but we still have a little bit of freedom. Do we choose NIE or do we choose linear combinations of NIEs? Okay. So, I will leave it at that. When we actually take a concrete 1D problem, you will see which one to do. Both are correct. Yes. Okay. So, the question is, we'll have to substitute this into the weak form E into I and NE into I times. Is that what you're saying? Yeah. Okay. So, let's actually write that down. Okay. So, we'll write down this weak form now that we have. So, what I'm going to do is substitute U into the weak form. Okay. So, E is equal to 1 to NE, that is the first term. The next term is I is equal to 1 to 2. Okay. Uie is a constant, it can come out of all integration signs. Will you agree? Uie is a number which I want to determine. So, it will come out of all integration signs. Then what is left is integration over element. Okay. So, we will call it integration over an element. Okay. Then I have a first term is Px dWmx by dx dNie by dx. This is the first term of the weak form, right. Second term was what? Qx remains as it is. Then I had a Wmx and I had a NIEX, right. Then I also had a Wmx f of x. This whole thing is integrated, okay. And what was left was the boundary condition terms, right. So, that is Px Wmx du by dx. And what are the endpoints of this segment? X is equal to x1e, x is equal to x2e is equal to 0. This is the weak form. So, all I have done is substitute u and I have kept w as w, Okay, so this is one equation, and how many variables will appear over here? As many of the ui's are there in this this whole segment over here, from here to here. There are various, there's u1, u2, u3, u4 and u5. All of these guys are there. Do they all appear in this equation? They all appear in this equation. So what I have written are global numbers, and these things over here, these are local numbers, but there is a one-to-one correspondence between local and global and global and local. Okay, so we can write it in either terms. So will you agree that this is one equation in 5 variables? One linear equation in 5 variables, because over here is everything inside this bracket known. F is given to you, Q is given to you, P is given to you, N1, I mean NIE you chose, WM you chose. So it may be looking complicated and ugly, but everything inside this is known to me. So what is the very first trick that I had learned to do this integration? Quadrature, right? So quadrature is a very greatly simplifying thing, because it does not need me to know the detailed analytical integration of whatever, right? I can increase the order of my quadrature rule and get arbitrarily good accuracy, right? In fact, your NIEs, they are linear polynomial. So integrating them will in fact give, with quadrature rules, will give you exact answers, as long as P and Q and F are well behaved also. Okay. So another common trick that is done is, because this discretization is going to be chosen to be fine, you can in fact substitute P, Q and F in terms of a pulse basis function. So you can assume them to be piecewise constant in each segment. So then these guys also just become numbers. For each segment, you just put in the value at the midpoint of P, Q and F. So all you're left with is a polynomial to integrate. Over here, the last term will be a linear term. This is a linear term, multiplied by this will be quadratic, right? So basically all polynomial terms, it's trivial to integrate them. Okay. So what remains now, of course, is I got one equation in 5 variables, and what would I do next? How will I get enough equations in enough variables? This guy, WMX is in my hand. I can put in different W's, get more and more equations. Okay, each W is non-zero in a different segment, so I'll get different equations, but all equations will have some combination of these U's. Okay. Now, so what we do is, substitute WMX for various values of M, okay, get a system of equations. Okay. Now looking at this, so I mean we'll take a detailed 1D example where we'll come up with the system of equations. So is there any part of this procedure which is not clear? Let's make it fully clear now. Yes, WMX will be from 1 to 5, where M is some arbitrary thing. M need not have a correlation with the elements or whatever. I mean, because there are how many elements? There are 4 elements. So M cannot be element number. M will be something else, such that I get enough equations in enough variables. That's my objective. Only then I can solve it, right? That's why I wrote that WM can either be NIE or some linear combination of NIEs. My basic objective is to get enough equations in enough variables. So how to choose these WMs, we will look at in detail in the following slides. Okay, but the basic idea here is enough equations in enough variables, that is the objective. Okay, so just put that aside for now. Now looking at this equation, we should be able to understand one very key property of FEM. Why do I get a sparse system of equations? Can you tell me why is it sparse? So as a concrete example, take Wmx to be, let's say, we'll just look at one equation. Okay, so we'll take Wmx to be this function. So this is element 1, 2, 3, 4. So this, what is the notation for this shape function? N, element number is 2. Left or right? Is that our convention? So let's see. So the first one, this first basis function, what is its value at the left node? 1, and it goes to 0, right? So what is this guy? It's 1 at the left node. So it is n2 of what? What is I? Left or right? So let's look here. This is, so n1e is, what is n1e? This is x1e, x2e. Isn't this n1e? Right? And what is n2e? The other way. Right? So now I have drawn this green thing over here. So what is it? So let's write it again. N, element number is coming at the top. Element number is 2. It's left or right? Left. It's 1 at the left node. So it is therefore 1 x. Okay. So I am going to choose Wmx is equal to n2. If you want, you can write this as E is equal to 2, I is equal to 1 x. Okay. I am testing the weak form with this shape function. Now can we argue that the system of equations I get is sparse? Let's look at the, how should we do this? So this second term, if I look at, let's start with the easy thing, the second term. The second term, Wmx, what is the domain of Wmx? Is only element 2, because this n, this guy I have chosen is non-zero only over E is equal to 2, right? So if I, if this E is summing over all the elements. So if this E goes to element 1, 3 or 4, what will happen? 0. Therefore, U1, U4 and U5, will they appear in this? They will not appear. They get multiplied by 0. So similarly, you can see the only terms that are going to be non-zero in this equation will be what? Which u's will be non-zero in this, will appear in this? E equal to 2, no, but which u's? You are right, E is equal to 2. E is equal to 2 has which u's in it? U2 and U3. Yeah. That will not be multiplied by?
So that will be separate.
Have I think I have missed a term over here. Have I? The last term does not have a U. Yeah, the last term does not have a U.
Brackets.
Square bracket. Actually, yeah, the square bracket should not include the last term, is what you're saying. Okay. Let me just check if I made a mistake in. Yeah, you're right. So this term you're saying should be like this, and so this will be dx, right? The endpoints for each segment will be there, right? So they, in fact, these endpoints will cancel except at the very endpoints of the
Whole domain.
integration over whole domain. Which term? This fx term?
No, the endpoints term.
Endpoint term is? It is included in the summation actually. The I summation is appearing like this. Endpoints, right? It's integration by parts. Okay, so anyway, this W fx term does not bother us because W, it does not contain any u's inside it anyway, right? So the u's that will come in this equation are only going to be u2 and u3, right? So you see that I did not get all five u1, u2, u3, u4, u5 I did not get in this one equation. But remember, in our integral equations, whenever I took any one pulse basis function, I got a dense system of equations. I got n equations in n variables, and each equation had all the variables. So it was a dense system of equations. Here you can see what is saving us is the fact that both the basis and the testing functions are subdomain. That is the first thing. The second thing, there is no Green's function which is non-zero over all segments. That was the reason why I got all non-zero terms. Here there is no global kind of a function that is connecting one segment to another segment. So only if there are shared edges or shared nodes is there any coupling. So this gives us a, so you can sort of extend this argument, choose Wm to be different terms. You will get, each equation will have only a subset of the total number of variables. So that's how you get an overall sparse system of equations. Okay.